Good morning, and thank you for joining us for our first edition of Zeeco's Thought Leadership Forum on Flare System Failures. We're broadcasting to you from Zeeco headquarters in beautiful Broken Arrow, Oklahoma. Today, our experts will be covering various topics ranging from flare and liquid seal design to maintenance and operations to flame detection, radiation, and much more. These topics were chosen by you, our audience today of nearly 500 people who flooded our inbox with hundreds of questions. While some of these questions did not come with pictures or videos, our team was able to pull together visual representations of each issue from our records to help facilitate today's discussion. In our 40 years in business, we unfortunately have seen more than our fair share of flare system failures and challenges, as well as results of improper operation. We hope that today's analysis will help mitigate or prevent these things from happening in the future. Before we dive into our discussion, I'd like to touch on what brought us here today. Since the pandemic hit, Zeeco has held more than 100 webinars to continue to reach our customers. A little more than a year later, we've presented to more than 6,000 end users and helped dozens of essential businesses continue operations despite the impacts and challenges of COVID-19. Although we've noticed a phenomenon in our industry and amongst our customer base, something we here at Zeeco like to call webinar fatigue. And this is the result of countless hours in front of a screen, listening to old people like me speak in monotone voices as they flip through PowerPoint slides they made back in 1987. We felt as though you could use a break from the repetitive nature of a traditional webinar, and with the size of today's turnout, it seems that our assumptions were accurate. Our goal for the Thought Leadership Forum series is to answer your burning questions in a more casual and enjoyable environment. So feel free to sit back, relax, and enjoy the content we've prepared for you. And so that's enough out of me. Let's hear from our panelists. And first we'll start with Scott Smith. And Scott, why don't you introduce yourself, and please remember that our marketing department has made us promise to keep this PG-13 or better. Scott?
Thank you. I'll work towards that goal. Hello and welcome. My name is Scott Smith. I'm responsible for Flare Systems products for Zeeco. I went to school at Oklahoma State University some many years ago. Got out of school and worked for an EPC company for a short time, then a chemical plant in South Texas, and have spent the remaining 40 plus years working on combustion equipment, primarily flare systems, and the last 21 years at Zeeco.
All right, so fun fact on Scott, we're going to look at a picture of one of the first flare systems that Scott worked on right when he got out of college. It's about a 96-year-old flare system, and Scott actually commissioned it. So fun fact on Scott.
Yeah, I used my Kodak Instamatic camera at the time to get that photo. It wasn't quite that long ago, maybe 42 or something.
Nevertheless, it's a fine black and white photo, Scott. With that, I'm going to turn it over to Doug Allen. Lead us out of this, Doug.
Okay. My name is Doug Allen. I went to the University of Tulsa. I have a degree in chemical engineering. I came out of school, worked in combustion ever since I left school. So my whole career pretty much in combustion. John Zink for a few years, and then Zeeco for the last 25.
So Doug represents one of our most tenured colleagues here at Zeeco. It's going to be very difficult to find someone with a greater breadth of combustion knowledge, particularly with flare systems. Although one of my most favorite memories of Doug actually involves an incinerator project he worked on 20 some odd years ago that took us all across India, which was kind of interesting. So thank you, Doug, and thank you for putting up with me for all this time. Okay. And with that, I'm going to hand it off to Clayton Francis. Clayton, why don't you introduce yourself for us, please?
Sure thing, and we do appreciate everybody that's joining us. I'm a mechanical engineer that graduated from Oklahoma State, and I've been with Zeeco for 14 years now, my entire time out of school, and worked with flare systems that entire time. And now have the opportunity to work on the engineered solutions group, looking at failures in equipment in the field and providing rectified equipment for that.
Thank you, Clayton. And Clayton, you may be the youngest guy on the call here today, but I'd also point out that you have the least amount of hair, which probably translates to dealing with some of the more difficult problems and failure modes. So while you may be the youngest, you're not without experience.
I have a bad roof. Apparently, that's the idiom in Brazil. Is I have a bad roof. I saw a customer a couple of years ago, and it had been a good 7 or 8 years in between seeing him in person, and he saw me and goes, "Oh, your roof went bad."
Well, I think the business you've chosen may play into a little bit.
Yeah.
So anyway, thank you, Clayton, and thank you for letting me have some good-natured fun. Finally, my name is Darton Zink. I'm also a graduate of Oklahoma State University a long time ago. I've been here with Zeeco since I got out of college 26-ish years ago, and I serve as our president and CEO and have been in this role for the last 21 years. And so enough about that and all of us, but I do want to make one special recognition, which is I'll introduce Clint Ellis. Clint is our technical event manager, and he works behind the scenes, and he's going to help us navigate through some of the content and media that we're going to be sharing throughout the presentation today. And so, Clint, why don't we go ahead and kick things off, and we'll start off with our first question. And the first question we have today is on the subject of flare operations. And the question is, it's a two-part question, actually. What is the most frequent operational failure in air-assisted flare systems? How can the airflow be controlled when the flare is in a normal state and when it's in an emergency state? And can an excess of air cause the flame to be snuffed out? And so I think we've got video that we'll look at of an air-assisted flare, which is not operating properly. So who wants to take this one?
So definitely the best way to control air for an air-assisted flare would be through the use of a VFD system to give you the greatest amount of range of operation, the best turn down, the best match with flare gas flow to airflow. Measurement of how to set that air rate could be handled many different ways. You can have measuring flare gas flow rate and use a ratio control. You could be pressure related. You can measure pressure in the flare header and relate that to a flow rate. Or some other things, Clayton, that we've used before.
Yeah, Doug, I mean, I agree. First of all, getting good turn down is in the air control system, and the VFD and maybe subsequent dampers is helpful. If anybody's been a victim of some of my other presentations and teaching, I talk about how turn down is one of the main killers of flare. This flare may have a turn down ratio of 10,000 to 1 on the gas side, but the blower in this case only has a turn down of 3 to 1, and you're gonna have really bad balance between the air and the gas. As far as control, I'm a fan of the optical systems. So an optical system really just looks at the quality of the flame. It really doesn't care what the flow rate or the composition is. So those two items can vary, but it can assess good quality flame, whether over aerated and too much air or not enough air and leaning towards smoke. So an optical system can replicate the function of a well-trained operator in that case.
So Clayton, in this video, why don't you just explain what we're seeing, or maybe more importantly, not seeing?
Sure. We always want to see a yellow luminous flame coming out of a flare if it's lined up and has process going to it. But we also don't want to see this smoke. This smoke, oddly enough, is from the over application of air. There's so much air, and the kinetic energy and the relative pressure at the flare tip exit is suppressing the flame inside of the burner. And so the process is burning in a substoic manner, and that's the coke and the sooting that's coming out from burning inside the tip. And it's a little counterintuitive, but less air, being able to cut back on air, would first eliminate the smoke and then allow the flame to come out of the tip and preserve the lifespan of that equipment.
Scott, you have any words of wisdom for us on this topic as well?
One thing also that customers might consider is to not get fixed on having a single blower with a VFD device. Instead of doing a single 100% blower, you could easily apply two 50% capacity blowers and apply your turn down to the 50% capacity blower, thereby getting a much lower air rate under normal conditions. It also gives you some ability to have a maintenance backup device, or in case you have a problem with one blower, you can shut it down and replace it with a warehouse spare, or still achieve a majority of your smokeless rate, your desired smokeless rate.
All good points. Looks like we have a second video that shows an air-assisted flare not performing as we would want. Scott, what are we seeing here in this video?
On this one, we're also seeing, as Clayton was talking about, over aeration of the flame. So insufficient control by the blower to turn down to the gas flow. And what's happening is the gas flow is being pushed back down into the flare tip, and it appears it builds up pressure and then surges and ignites, and then the air from the blower then again overcomes the pressure from the gas and pushes it back down inside. So classic Indian smoke signals from a flare here, only not caused by a liquid seal drum, which you might have seen in other applications.
Scott's descriptors never cease to amaze me. Doug, any last thoughts on this point?
No, just as Scott said, just controlling the fan. Definitely we're over aerating this flame, causing it to be pushed back down in the tip. So,
all right. Let's move on to the next question. Next question is one that it's a simple question, but maybe a more complicated answer, which is, in which cases should we use center steam? Let's see, Doug, you want to lead us off with this one?
Sure. So center steam is fantastic for helping to prevent burning inside the tip, and in flare systems where you have leaking relief valves, you have small amounts of flare gas that are getting into the flare header and being carried along with the purge gas, are burning and maybe creating a little bit of smoke that, when using upper steam, like we see in the picture, would cap or force the flame back down inside the flare tip. The center steam could basically make it smokeless through a dilution process. So that would be the times when center steam is most useful.
Clayton, you have anything to add on this point?
Yes. Additionally, as the flare tips get larger and larger, then it becomes more necessary to apply center steam to prevent burn back. So that, again, we see in this picture a significant volume of steam coming from the perimeter injection at the top, and that has some significant velocity and pressure and can help prevent the purge gas from coming out. And so if you have center steam there to promote that the purge gas coming out the top, provide some buoyancy and some velocity, it will preserve the life of the tip. And we see the bluing of this steel, which tells us that there's been some long-term residual burning on the inside. As flare tips get larger and larger in diameter, these steam flares, that becomes more necessary. The propensity to stabilize inside becomes greater. The damage becomes accelerated. So from 24 inches and up, I like to start considering and sometimes requiring center steam to make sure that we preserve the mechanical integrity of that tip.
All right. Scott, anything else?
No, it is interesting. The bluing on the tip is likely located right above where there would be a velocity seal or purge reduction device down inside the tip. So it's somewhat protecting the flange area from getting too hot. And I also noticed that this platform has our new rapid egress feature for going back down to grade, which
Yeah, I'm not sure that platform should still be OSHA compliant in the latest reading of the regulation.
that doesn't really look like it. No.
First step's a doozy.
That's right. First step's a doozy. Shouldn't joke about it, but that is a good observation, Scott. Let's move on to next question, which is, do you have data and models to predict flare performance under purge conditions or low flow conditions, especially related to combustion efficiency and the net heating value calculation? And what are best practices, the NHVCZ, and what are the best practices for low flow operation? So Scott, what would you comment on this particular topic?
There has been a lot of testing and a lot of evaluation done over the years relative to flare performance and destruction efficiencies. The new federal regulations that evaluate based on net heating value in the combustion zone definitely give a basis, a good basis for the amount of assist gas you would need or paring back on the air or the steam in the combustion zone to ensure that you're getting high destruction efficiency. But in reality, and what we see a lot of is through the subject matter experts from a lot of the customers we work with, and has been true since the testing in the early 80s, is stability and having this, as Clayton mentioned earlier, having this yellow flame in the combustion zone is a tremendous key to ensuring that we're having high destruction efficiency. If you can see even a light yellow flame on the flare tip, it's almost assured that you're achieving a fairly high destruction efficiency. Your control modes, in fact, the TCEQ have some documents out in the industry that show you colors of flame versus proper operation, which are excellent tools for operators.
Okay. Doug, what else would you add on this topic?
Pretty much the same, along the same lines. I mean, purge gas, we know that's metered. We know the flow rate of purge gas. Usually the cooling steam rate as well is metered through orifices. So we know those combinations. We can easily calculate the combustion zone net heating value and make sure we stay within the range. The trouble comes when you have some release of something else into the line, which is what looked like was happening there. We had something that smoked quite heavily, which is not a normal purge gas typically, and coming in cyclic manner. So that makes it a little bit more difficult, but measurement of your flow rates and setting your ratios based on those measurements are some of the best things.
Clayton, you want to touch on anything else or instrumentation around this?
My answer is a lot the same, that we can control optically, and that helps. It automates and gets us to a healthy combustion flame. The comment or this advent of NHVCZ is something that really helps us. Prior to the research and the suggestion of NHVCZ, it was a much more difficult answer to know what is good combustion. And so I think NHVCZ and NHV dilution ratios really are a helpful operating parameter that lets you know you're meeting good combustion parameters.
Okay, well, along these lines, next question is, to what degree can steam be reduced to also minimize the amount of purge gas added to the flare while maintaining NHVCZ above the limit. Who wants to take that one?
So definitely we see a lot of times where the steam control valve is not pulled back, completely closed, and allowing just cooling steam to go to the flare during purge or during very low flow rates. There's a tendency to hide that flame so that we don't upset our neighbors, and that mode of operation can cause lack of DRE, quenching of the flame, those types of things. So definitely controlling that steam valve, keeping it down at minimum when it's truly no need to add steam to the system, and allowing the visible flame that Scott talked about. TCEQ is one agency recommends that you have visible flame at the top of the flare. Those are all good things to remember in operation.
And to Doug's point, I mean, kind of a memorable service call that I personally made about a long time ago now was with a client in Asia that basically put the minimum set point on their steam control valve such that it added enough steam to make the flame invisible at their purge rates, which were quite high. And while this probably got management off their back for having purge gas that was visibly flaring, unfortunately, these were on tall stacks. They were getting the smell of unburned hydrocarbon in the town about 7 miles away. And turns out the way to solve that problem was simply to turn the control valves down to what was actually needed for smokeless burning and purge conditions, and it solved the problem. And I spent the next 2 days convincing this client's management that visible flame was actually a good thing when it comes to destruction efficiency. Scott or Clayton, do you have anything else?
I certainly don't envy the position of operators because somehow the public really needs to learn this and understand that. And that's a difficult proposition. That like in the video that's showing right now, the flame on the right is the highest level of protection. It's the highest combustion efficiency. It's the safest. It's the best operating for the tip, actually. But it's also, from a public perspective, may not be the most desired. But it is correct. So it's part of this is going to be a public education endeavor as well.
Okay. Scott, anything else you want to chime in on before we move on?
I remember I gave a presentation in Houston once about this subject, and I actually flew down and drove around through along the ship channel for an hour or so that morning and took some photos, some 12 or 13 photos of elevated flares, all of which were significantly oversteamed, none of which had any visible flame on them. And that was at the same time TCEQ was using helicopter air sampling to get ethylene percentages. And it was kind of the start to some of this work on proper control for steam and visible flame. So been a problem for a long time, and hiding the flame has always been the goal.
And it's the opposite of what should be done from an emissions and operation perspective.
Yeah.
Okay, and next question that we had comes, I'm assuming, from Colorado, but the question is, Colorado has recently been implementing new requirements to combust hydrocarbon effluents and avoid venting to atmosphere. For any combustor or flare system, they require flow measurement and control. Can you manage flaring of hydrocarbons at low pressure, which as defined here is less than 3 psig, rich gas well enough to avoid smoking without adding a blower?
Yeah.
Scott, you want to address that one?
Sure. Definitely in a combustor is mentioned. So definitely in closed flares are enclosed combustors, we can handle the smokeless combustion of even very heavy saturated hydrocarbons and even more complex hydrocarbons, propylene, butylene, without assist medium of any type, such as a blower, and using the draft in the chamber to inspirate air and provide smokeless burning. On an elevated flare in a wind with a very heavy saturated hydrocarbon, that would definitely be more difficult and might need some type of an air assist from a blower. But in a combustor, it's quite easily achieved.
Doug or Clayton, you want to add anything else?
Well, definitely, you could also use gas assist if there is high pressure gas available. So gas assist, so injecting it much like you would steam or air would also be a method. And then in some cases, just the porting on the tip can help dramatically lower the amount of smoke, and then very little assist may be needed. So we have lots of options, definitely something that's possible.
You say you see gas assist and pressure assist pretty common and popular in upstream and in some midstream applications.
Yeah.
All right. Next question is, how do you ensure flame out does not happen when a large volume of processed gas is released in a short period of time to the flare tip? So in other words, how do you keep the flame from going out when you hit the flare tip hard with a large amount of gas flow?
Okay.
And so Scott, looking at the photo we have here, I'm guessing this is something you did not design, but you want to kind of comment on the overall topic and the photograph we're looking at?
So this is a good example of an air-assisted flare tip, and in this particular design, the gas is coming through the arms that you see there. I don't know if Clint can designate the arms, but the arms are the part has the plate on the end of it, right there where the pointer is. And between the arms, and also between the ends of the arms and the wall, is where air is being supplied via a blower located at grade. So you have gas inside these main arms, and then you have air coming up between the arms and mixing with the waste gas. So one of the key points of this type of design is you have to have the pilot located right at the end of one of the gas supply arms. So unfortunately, in this case, when they were installing the center part of the flare tip assembly and welding it to the riser, it looks like they've gotten off by a few degrees, and they have the pilot located at a small pilot bridge, but it's bridging over into the airstream. So it's going to be real difficult to get a combustible mixture at that point to ignite that flare. So this flare would definitely have a propensity to not ignite until you had quite a bit of hydrocarbon in the atmosphere around the pilots. Could light off pretty hard.
Yeah, this would be, I don't know whether this is an installation issue or a design issue, but this would be what you wouldn't want to do if you have a high flow, quick release scenario. Clayton, do you have a comment?
Yeah, it's definitely got an alignment issue, but it highlights some of the technologies that can be employed. Good stable pilots with, in this case, a flame bridge, but flame stability platforms or flame tabs are described in API 537. We employ some other stability mechanisms such as sonic boxes. And when you have the right equipment as part of the flare tip design, it can take a shock of a huge increase in capacity over a short amount of time and maintain stability. Unfortunately, the installer defeated those mechanisms in this picture, but it is possible when you correctly incorporate the stability mechanisms. It'll go from 0 to 100 with correct stability and ignition.
Doug, anything else you want to add or chime in on?
No, I agree with Clayton. It's stability point, knowing where that stability point is, proper positioning of the pilots. We've done a lot of testing here at Zeeco on this very subject. And yeah, it is no problem for us to open up 60 plus pounds of pressure to a tip and get immediate ignition and stability. So just have to have the proper design.
Hey, Clint, if you wouldn't mind, go back to that photo one more time. One thing on this one that's interesting is down there on the side, you can see what looks like the use of maybe flexible conduit or PVC coated conduit. I can't really tell, but yep. One installation issue that we see happen in the field is people put up flexible conduit that's not really watertight, or they use flexible conduit that's coated with PVC, which burns off very quickly. So that's one thing you absolutely have to be aware of at the top of this flare, is that all of that's going to burn off and go away in a short period of time and will cause any high temperature wire inside there to become water soaked and fail. So just a point of installation and design.
Okay. Clint, I think if you go on to the next photo that you previously had up on the subject of stability and large amounts of gas flow going suddenly, great example of that's a multi-point ground flare, where you've got, in some cases hundreds of burners that are staged, and you hit those burners with the maximum design flow pretty much all at once, and that's how they're supposed to perform. They work that way day in and day out, as a slightly different example of how flares can be designed to take a maximum flow suddenly. Anything else the group wants to add before we move on?
No, I think that's good.
Yep. And the last item I have under the subject of flare operations is this one, which is how do you solve pulsation in a flame? And so we've got a video that shows a big pulsation in a flame. Pulsation in flaring can cause a number of issues, noise being just one of them. But Clayton, you want to take this one first?
Yeah, in this instance, the operator's pretty fortunate that it's not pulsating to a point that it actually smokes. We see that sometimes where it goes from a very low flow to a high flow, and that high flow will actually produce a smoke signal as well. A lot of times when we see this range at this frequency that you can see on the video, it's a liquid seal issue, that there's sloshing in the liquid seal, and that movement of the water opens the gas, the gas downcomer, and then closes it back up as the elevation goes up and down and undulates. And so that can be solved with, we've got some methods for making the gas relieve out of that downcomer more evenly and won't create these pressure waves. Extra baffling, going above and beyond the API definition for what that screen and distribution looks like is really helpful in calming this down. And then pragmatically, if it needs to go away and you don't have an opportunity to fix the liquid seal, then lower this liquid seal level if appropriate, to stop that water slosh.
Yeah.
Yeah.
Anything to add?
Yeah, I mean, so API 521 and going into 537 makes some small statements about preventing of pulsation just based on the diameter of the drum, but there's a lot more to it, just like Clayton said. I mean, it is the distributor that's inside, it's the baffling that dampens the water movement. So it's much more complex than just setting the drum diameter. So we'd be more than happy to help folks with that, have this problem. We've dealt with it quite a few times and successfully.
Scott?
So pulsations, in this case, as Clayton mentioned, this looks a whole lot like a liquid seal problem, but just keep in mind that this pulsations can also be caused by over aeration, as we saw in the video earlier. It can be caused by over steaming, where you're capturing the gas and the gas is building up pressure and punching through the steam cap on a repeated basis. It could even be, I've seen systems where it was caused by relief valve chatter or relief valve cycling way upstream in the flare system. So liquid seal drums are definitely a major cause, but for sure this similar pulsations can be caused by other operating issues also.
Yep.
For that over aeration, and it's, I don't know, it's become more prevalent here recently as far as what I've been attuned to. It seems like 3 to 6 hertz is that combustion instability rumble and pulsation. And so that the video should look like about 1 hertz or so as far as what the 1 to 2 hertz. But that pulsation's a little bit more frequent when it's over steaming and you see a consistent flame. So yeah, there's definitely a difference in those and different root causes that we can help assess.
Very good. Well, I'll take this opportunity, since we're talking about liquid seals, to move into the next topic, which is on liquid seal design and operation. Just have one question on this topic, and the question is, what are the specific applications for liquid/water seals in the bottom of flare stacks? In most flaring scenarios, these seals blow off and need to be reestablished before startup and are a big hassle where a reliable water source is not available. Scott, why don't you take this one to start?
So liquid seal drums are something that are commonly used in refineries and chemical plants. And in many cases, they are used to produce a back pressure on the header. That back pressure on the header can be something very small, 4 inches of water or 6 inches of water, just to ensure that oxygen doesn't enter the header due to a negative pressure at the base of the stack caused by draft. But it can also be much higher, 20 inches, 40 inches of water, 60 inches of water, when it's used as the back pressure for the suction of a flare gas recovery compressor. So common uses on liquid seals are typically in systems where there are lots of relief sources, lots of headers, and it's a safety mechanism to prevent air from coming back into the system and also to produce this back pressure on the header. The video is one of a very small flare system on a small plant, and the liquid seal drum is sized per API requirements, but the liquid seal drum is there to protect the system during purge flows, during very low flows, and as was stated in the question, during a maximum relief flow, the liquid is essentially all carried out of the seal drum and either dissipates into the flame or becomes a mist out of the top of the flare tip itself.
Yeah, this one had a glycol, because of the temperatures, a glycol water mixture to keep it from freezing. So made it even more visible, the liquids, as opposed to being evaporated in the flame. So oftentimes it could happen and the water doesn't come back down. It just disappears into the atmosphere. But in this case, the glycol allowed it to come down and make a nice pattern on the snow.
And this one was unusual to even have a liquid seal in reality, because most gas plants, of which this is one type, would typically not even have liquid seals. LNG plants never have liquid seals. So liquid seals, as I said, are primarily a fixture in refineries and chemical plants, but they're used in a lot of applications. We did have a second photo here. If we were talking about the question also was asking about quick refill of a liquid seal drum, and this is an example of a drum that actually has a water holding chamber in the top of the drum. You can see towards the top cone there's a max LL noted on the right hand side. That's showing actually the liquid level in a donut of water up there in the top of the drum, where the normal liquid level straight down below that is on the liquid seal portion right down at the base. On this drum, if you have a major relief and it blows all the water out of the drum, there's interconnecting piping that drops all the water out of the storage portion in the top, and you can reseal the drum and reseal the liquid level within just a few minutes using just a dump valve. So it provides the refill very quickly if you don't have a high volume source, such as a firewater line or something like that near the drum itself.
Good. Okay. I'll move on to the topic of general flare design. And the first question is that in many cases, too much steam injection is used to avoid complaints, i.e. visible flame. Is a ground flare the only solution to hide flames? Who wants to take the first stab at that?
Well, definitely ground flares are the most common choice. If your goal is to hide the flame from visibility, then an enclosed ground flare and a multi-point ground flare are two fantastic ways to do that. Because any of the elevated flares, being steam assisted, air assisted, no matter the assist media, as we've been talking, I mean, you have a flame at the top of a stack. We want you to have a flame. The flare needs to have a flame up there to have good destruction efficiency and good performance for the environment and everyone else. So really, if you must hide the flame, and there are definitely times when it's good, being a good neighbor is important, and hiding that flame is important. So enclosed units are definitely one of the best ways to do that.
And one of the things I'll just add onto that, Doug, oftentimes an enclosed flare can be used in combination with an elevated flare. So you can take a certain amount of your design flare system flow rate into an enclosed flare for normal operations, and then if you have an emergency case that's much higher, it can then be staged into that elevated flare. And the enclosed flare that we were just looking at as an example, this was actually put into an INEOS ethylene plant in Scotland many years ago, taking the place of elevated flares, or the flow rate that would go to the elevated flare during normal startup and shutdown operations. And the local community that was just across the road from the plant went from protesting quite aggressively during any time they had a scheduled startup or a shutdown and the associated flaring, to going to a scenario where they never knew it was happening. Because not only does the visible flame go away, but also the associated noise and obviously the light as well. Scott, you want to talk a little bit more about multi-point ground flares and and other methods that we can use to flare with while hiding the visible flame?
It is interesting how the concept of a totally enclosed refractory line flare has become more and more popular over the last 10 years. We're working on units in England and also in the UK, up in Scotland and other areas of the world, and have put them in Thailand and many other countries, Russia, lots of places. Initially, they were being used primarily in areas with just very dense populace, but now they're becoming more used even in other applications. Multi-point ground flares can achieve the same restrictions are on viewing of the flame at much higher flow rates than most enclosed ground flares. Closed ground flares are limited to something like 500,000 pounds per hour, but many of these high pressure multi-point stage ground flares are sized for 2 million, 3 million, 5 million pounds per hour, and can move that huge visible 700-foot long flame down to the ground and enclose it in a perimeter fence. So definitely a viable option for many applications.
Yeah. How does that jingle go? To help with your neighbor, Zeeco is there.
That's a new jingle. That's pretty good.
Yeah.
Doug, I'm going to suggest, appreciate you sharing that. You don't need to sing it. But,
Yeah, definitely not my thing, singing.
just because you're working on a marketing project doesn't mean you've moved into marketing here, Doug.
Doug, you are and will always remain technical.
Thank you.
I mean that is a compliment. We've had next question is that comes from a customer. We've had lots of issues in recent years from noise complaints from the community. This is largely due to a low frequency rumble during heavy flare operation. Are there strategies or improvements in flare tip design to address this? And why don't I give this one to Clayton? Why don't you lead us off on this question?
Certainly, that rumble again is a combustion instability. It's almost a detonation. It's a time when the flare is either leaned out and over aerated and kind of extinguishes and then gets a volume of gas and reignites. That's the case in elevated flares, and most common in steam flares, but I've seen it done with air flares too. You get that really low frequency pulsation that travels for miles. There you can have complaints 10, 12 miles away. It can be done, or you can create that scenario with enclosed flares as well, where you actually starve the enclosure of air, and so it suppresses the flame, and as the flame extinguishes, then the stoichiometric ratio becomes appropriate again, and it relights, and you get that rumble. So it's all about control of air, although steam is how we motivate air into the combustion zone, so it's control of steam as well. Control is the number one key to resolving, but also there's some stability aspects that can be added and incorporated to prevent it. I know Scott and Doug have parameters on, as we design flares, for making sure we create an entire profile across that tip that has good stability and ignition.
Doug or Scott, you want to pile on?
Definitely, I'm with Clayton on enclosed ground flares and controlling that air, matching the air into the unit with the fuel that's going into the unit. You can definitely get some instability points there, but it's just simple control that can easily be handled. And then design of the elevated flare equipment, positioning of steam tips and air nozzles, and all of those things play into making sure you have a good stable base for the fire and eliminate the rumble.
There are some designs out in the market that are more prone to this than others, but and Clayton said this earlier, and I totally agree. The the cure to this is control, and probably the absolute best method, again, is some type of an optical control, because if you can control the steam properly to get that yellow flame or orange flame up on top of the tip, the noise problems will 100% go away.
And just to touch on one point that I think Clayton mentioned just slightly, the stability of the flame, particularly in an enclosed flare, or I suppose in a multi-point ground flare, is critical to preventing that rumble or low frequency combustion noise. Anytime you have a moving flame front, even a little bit, where it's not stable and anchored to the burner, you have the opportunity to have that kind of problem. My dad, who invented the first enclosed flare, as far as I know, in the world back in the 60s, had a problem at a job site in Europe where they actually were rattling homes 7 miles away from the plant with this scenario in an enclosed flare, and modifying the stabilization device on the burners in the enclosed flare solved the problems instantly. So it's proper design, whether it's on the control end or the flame stability end, is generally the route to go to avoiding these types of issues.
Yep.
See, next question. What is the recommended flare type or design for smokeless flaring at offshore platforms where steam is not available? I'll go to Scott on this one.
So there's quite a few, actually. Most offshore platforms have flare gas that is coming from their separators, whether it be LP, MP, and HP. It's coming out of their separators at various stages. But one thing that is typically common for most all offshore flare systems is the pressures coming out are fairly high. So we have, and there are available in industry, a whole range of flare tips that are using the pressure and the exit velocity at the tip to achieve smokeless flaring. And it can be either a fixed orifice type with a lot of very small nozzles that inspirates a lot of air and provides for smokeless combustion, or it can be what's known as a variable nozzle, a spring-loaded nozzle that actually holds the back pressure until a certain point and then starts opening to maintain sonic velocity at the tip. That also inspirates large amounts of air and provides for smokeless flaring. And even as Doug said earlier, we can use high pressure fuel gas, you can use high pressure nitrogen, you can inject other mediums to produce smokeless burning.
All right, Clayton, you want to add on anything?
We have this Varijet pictured, and one of the, again, I apologize to people who've heard me say this before. I feel like I say it ad nauseum, but turn down is the #1 killer of flares. And so by optimizing the exit area for high pressure through a variable technology like the Varijet, you have a secondary benefit of making sure that the exit area is appropriate for the flow rate. You have better turn down. That's why the flame quality is great, but side benefit, it lasts quite a bit longer. It's a much more durable piece of equipment.
Doug, anything else? Doug, I think you're muted.
Sorry about that. The shop was getting the flare tip to be perfectly round, and I was afraid it was the sound would overarch y'all's discussion. But so it is. I agree with Clayton. It's about varying the area. Definitely on an offshore facility where you don't have steam, may have limited power, pressure assist is the way to go. So using a Varijet, an MJ, or gas assist if it's a low pressure release is definitely the solution here.
And this type of tip uses a spring design that can go through tens of millions of cycles. It's quite impressive. There's a lot of data available, and this concept has been around for a number of years, primarily for use in offshore flare tip applications.
Okay, we'll move on to the next topic. This one is on chemical properties. And the question, will you please review or discuss a bit around plants and sites that have very corrosive materials such as ammonia or H2, SO4, etc.? What effect do these chemicals have on flaring, flare tips, and flare systems? So Scott, you want to take this one?
So this is kind of an interesting photograph here. I've got a couple of photographs here, but this one is really interesting. This was an Incaloy 800 flare tip that had steam assist and was in an acid gas, hydrocarbon acid gas service, and was returned for some maintenance or refurbishment. But what's interesting about it is when it was returned, you can see on the far left and actually on the far right at the very top, there's a flame retention segment that is still in place right there at the shadow. And yet the rest of the flame retention segments are all completely gone. And upon evaluation, the flame segment that is there was actually 310 stainless steel, although it wasn't supposed to be. It was supposed to be all Incaloy 800 materials. And this gives you a pretty good representation of what happens with Incaloy 800 material in a hot, fuming sulfur environment. It just is not suitable for that environment, and 310 is definitely a better material choice. And like I say, there's several photos here, and they're all showing that one is an air-assisted flare where it was wet, high sulfur service, and the flare tips actually lasted, I think, Darton, a matter of a few months in the initial installation and service.
This was an interesting project. This is a gas field in Qatar, where they were converting at the time. They were converting all of their utility flares to smokeless air-assisted flares, and they wanted them to last a long time. And they specified they wanted Incaloy 800 material in the tips because it was, in theory, good for a higher temperature than 310 stainless steel. At least that's my recollection of the rationale at the time. And for this reason, we pretty strongly recommended that they consider different materials. But ultimately, this is what the client required. And I want to say the flare tips lasted certainly less than 6 months. In some cases, it looked like the material just vaporized. It was gone. And we went back and replaced them with identical design. Everything dimensionally was the same, but just at a 310 material. And those tips are still in service today and have been for 15 years. It's just amazing how the material of selection can yield such a vastly different results in an environment where they had, in this case, they had a lot of H2S in their gas.
And that was originally a pipe cap, and the next photo shows some of the arms and the deflectors having just completely gone away also. So it's something we see a lot with, and this has all been discussions about H2S. We don't see a lot of corrosive results from ammonia. Ammonia is fairly easy to burn. There are other compounds. The next photo is kind of an interesting one because it has it's looking at a flare tip which was in an FL service for fluorides and fluoric acid, and it was completely eaten away. You see that steam manifold is just completely porous and just somewhat of a mess. But
this was one of those flares that Scott supplied in 1924 early in his career.
Actually, I don't think this one was there very long, actually. But then I think the next photo is one that Doug had that was really unusual. But
yeah, we never did determine exactly what was going on. It reminds me of what was that movie, The Blob?
Yeah,
this looks like science fiction.
Yeah.
This flare tip was abducted by aliens here.
Yeah.
We do see in U.S. refineries, there are still some legacy plants that have HF alky for their alkylization in their gasoline plants. And the HF is never supposed to make it to the flare, but inevitably some of it makes it at every plant. And so for HF, we do have to consider what materials we're going to put up there, and using Hastelloys or HR. We've got some exotics that don't make it impervious, but they make it more durable. But it's amazing what isn't supposed to make it to the flare that ultimately is probably going to show up over a number of years.
And it's about the only time we use the C276 materials is when we have HF or other really aggressive options, because it's just impossible to build something that will. All of the books will recommend that we use plastic or fiberglass.
Glass.
Yeah. Yes. Yeah.
That doesn't work very often, very fast, very long anyway.
Fortunately, that creates a problem for temperature.
Yeah.
It does.
When you have the compounding problem of temperature and the thermal challenges and thermal cycling with a flare system, and you throw chemical attack on top of that, you get some interesting challenges that come along. All right, let's move on to the subject of internal burning. First question: why do hot spots form below the burner tip, and what are possible reasons, and how do you remove these hot spots? Let's see, Doug Allen, you want to take this one?
Sure. Hot spots occur due to internal burning. So that's definitely our cause, and we need to find out, for burning to take place, we have to have fuel, air or oxygen, and temperature. And we need to find out where we're getting all of those things to create that burning down below. So hopefully we can look at our purge gas rate, make sure that we are purging with something that does not contain oxygen and is the appropriate rate for the flare. Maybe it has a purge reduction device such as a velocity seal or a gas seal that would allow it to use a little less than a tip that did not have any seal. But we want to make sure we're purging at a rate that keeps the air from migrating back down into the flare tip. Unfortunately, the ignition source is right there with our pilots and everything. So that's something that we're going to have a hard time eliminating. But if we can get rid of make sure our purge rate is correct and make sure we don't have any oxygen in the purge gas, that's going to take us a long way to keeping that flame up out of the tip.
I would say that we certainly want the flame out of the tip, but it can happen. You can have flame and internal burning inside the tip. What becomes much more urgent is if you have any evidence of internal burning below or upstream of your purge reduction device. If you have the base of the flare tip has a velocity seal, or if you have a molecular seal and you see evidence of internal burning and high temperature upstream of those devices, that's a very urgent situation. And it happens to be what's depicted in this picture. There's the flange, the inlet flange to this flare tip. Immediately downstream of that flange, literally 1 foot above is going to be the velocity seal. And to see high temperature from burning of the paint and rusting below that or upstream of that means that there's a significant issue. You're getting oxygen, sufficient oxygen to sustain combustion from the plant itself, or a hole or some kind of failure at the flare tip. And that can be more serious.
Anything can really, what you have to have present to have this internal burning is obviously a combustible gas with oxygen and an ignition source. And you've assured a great ignition source with your pilots at the top, but and this is showing oversteaming, and that's probably part of the problem. But we had a flare tip on an offshore platform in northern Atlantic where the winds were 40 to 45 miles an hour all the time. And the designated purge rate was something probably more suitable for 5 to 10 miles an hour. And they experienced significant burn back only because of the high wind conditions on that flare tip. So there's lots of factors that can cause this that need to be mitigated through operation and proper design.
And generally speaking, the larger in diameter the flare tip is, the more careful you have to be with regard to the subject of internal burning. And we talked earlier a little bit about center steam and how that can help mitigate the internal burning likelihood.
I have to believe with this piping configuration that there used to be a buoyancy seal at that position that happened to be removed and replaced with a pipe, it looks like.
Yeah.
There used to be. And this, I didn't think about it earlier, but this is actually a result of HF. This is an alky plant, and the HF attacked the base of the flare tip, and there's a huge gap that air was ingressing upstream of the velocity seal, which sustained that combustion.
All right, let's move on to the next one. We kind of already covered this, but how do you fix internal burning, and what kinds of preventative measures are considered while designing a tip?
This one is really manifest because of the type of purge gas. A lot of refineries are using refinery fuel as a purge gas, so that hydrogen content takes very little oxygen in order to stabilize and create some heat. So if you have a problem such as this flare tip, maybe a costly measure, but converting from a refinery fuel gas to a purchased natural gas can really help elevate that internal burning problem. And center steam the correct control and application of center steam would help this a lot.
This one looks like a bypass on a thermal oxidizer stack. Is that, I know we supply tips as bypasses for thermal oxidizers on occasion, but.
Yeah, definitely piggyback on another stack that appears to be just an exhaust stack.
Yeah.
Right. All right. For next question, for an air-assisted flare, is there potential that the assist air can flow back down the gas riser and cause an explosive mixture? I would say, based on that photo, the answer is yes. But,
yeah.
Let's ask the group for a more technical answer.
Yeah. Well, so this is a case where I think the fan may have been turning backwards. So instead of the air flowing into the gas riser, we were actually pulling fuel into the air side, and managed to create a stable flame that made it all the way back to the fan. So definitely check the direction of your fan to make sure that your air flare is pushing air, not pulling air, before you get it started up. But in answer to the original question, it is possible. We've studied this quite a bit on some of our flare types to find out that, the top of the flare tip at purge rate is really acting like a low pressure zone. And so the air, if you don't control, especially if you don't control your fan well, the air coming up across the top of that or beside that tip will roll over on top of the tip, just like any other flame stability device, and air will move down into the inside the tip. Now, back down the stack, we don't see that. I mean, you'll have a purge reduction device, losty seal, you have something in there, you'll have purge rate. So getting it back down in the flare stack and an explosive mixture, no. But burning inside the tip definitely can happen, and proper control of that air flare is important.
Right. Any other comments or points on that one?
I've run into end users who are very concerned about the potential of gas coming out of the air side, but we don't see that happening. With air-assisted flares that are elevated, the fan's always blowing. That fan is always going to have positive movement and pressure. It'll keep the gas from coming down. Even at high flare rates, the momentum of the gas and the buoyancy of the gas coming out is going up and away. So being at the base of the flare stack with the fan running is no risk. We're not going to see any. I get that question. It's not really the question that's written here, but it's a question that I get is there possibility of gas ingress down at the fan? And there's really not.
Clayton, you'll make a great politician. You answered the question you wish you were asked. All right, moving on to the next topic, which is liquid carryover. And first question, why is a knockout drum so important in a flare header? Scott, you want to take this one?
Well, we make flares, and most flare systems around the world are designed for either handling 100% gas going to the flare with maybe some very small entrained liquids, or they're designed specifically for 100% liquid. If you're really designing a flare for two-phase flow, it almost has to be a burn pit of some type, so that the gas ignites, but if it has liquid slugs, the liquids can burn in a pool in the burn pit. Knockout drums simply eliminate the concept of liquid carryover to the top of the stack, and I suspect that there's lots of videos out there in the industry showing situations where knockout drums either overfilled or knockout drums weren't present, and the liquid was allowed to go up to the top of the stack, and it typically doesn't just burn like gas. It can come running down the flare tip, and it can come running down all the way to the ground. It can drop out and ignite the grass nearby, or cause tremendous amounts of damage. So if you can imagine one of these located in a plant where it was operating with liquids overflowing out of the flare onto the adjacent equipment and personnel, that would be a tremendous safety hazard.
Correct. Yeah, I've seen in lots of videos over the years where you have a flaring event and the gas is flaring up, and then you get a slug of liquid come up and then come right back down, and the flame totally engulfs the entire
I think this video is interesting because it shows liquid coming out of both of these flares and basically engulfing the whole. This is the scenario you absolutely don't want to see happen.
Yeah, that is that's frightening.
There's been a couple of instances that we've seen with knockout drums not have this just catastrophic one-time overwhelming with liquid, but with two-phase flow. If it's undersized and you start to get some of that two-phase flow, none of the pipe work of the flare is really designed for that, and you can get some harmonics and vibrations that even if you don't cover the whole thing with liquid and fire, you can shake some stuff loose and create some problems in a short amount of time as well.
And generally, it depends a lot on the type of flare. A sonic velocity flare, similar to the Varijet or spring-loaded nozzle one we saw earlier, or a multi-point ground flare, those can take quite a bit of liquid because they offer some mechanical atomization, allowing those droplets to become extremely small and vaporize in the heat of the associated gas that's carrying that liquid to the flare tip. If you've got a flare tip designed for a low exit velocity and you have liquids carried up to the top, this is the scenario you're going to get. There's just not enough energy or velocity to cause those liquid droplets to break up and burn in the gas cloud itself without falling out.
Correct. Yeah, there's
another liquid overflow situation. Didn't make it to the ground, but
got close.
Got close.
That was maybe that's how Clayton lost his hair. He was down below and got a little too close.
The phone calls after those events are enough.
Sorry, Clayton. I saw my shot. I had to take it. Is there anything? Next question. What can be done with regard to the knockout drum or important design considerations in the knockout drum to prevent or mitigate this kind of scenario?
Well, we definitely need to understand the flow rates that the flare could experience so that we get it sized properly. One other unique thing in this particular picture, we see an inlet in the center and two outlets, one on each end. But one mistake I see happen commonly, excuse me, is that people will do the proper calculations to predetermine the size of the knockout drum, but they actually, when they specify it, they give a tangent to tangent or an overall length on that drum. But as you can see, the inlet pipe is there in the center, and the two outlets are not really at the tangent of the drum. They're farther back towards the center. So the actual time, because a lot of these drums are sized on residence time, we're cutting short that residence time, how it's actually built from the dimensions that it's calculated for. So make sure that we use the proper sizing or specify the dimensions in a proper way if it's a horizontal drum like this one. And then vertical drums, you have to be real careful because they're either going to use centrifugal force or actual stilling. You have to get the gas flowing slow enough that the liquids just can't be carried and they fall out. So,
and there's some ways to mitigate some of that with internals and other options, but you just have to get it sized correctly. You have to anticipate the liquid holding volume of the drum. You have to get removal pumps with backup removal pumps that are set up to ensure that you don't overflow the drum. But overflowing a drum one time is a massive problem for any facility.
Right. We'll move on to our next topic, which is on cold climates. And the first question is, can we have a discussion on very cold temperatures and center steam? So who wants to go?
They don't often go well together, unfortunately.
We can have a discussion. So, it's not an easy one, but we can definitely have a discussion on it.
Yeah, definitely. If it's a climate that's has warm summers and very cold winters, maybe in the wintertime we talk about changing the steam out to some other media, nitrogen or something, not compressed air. We don't want to necessarily put air in our flare tip. That's going to cause the same problems we talked about earlier on internal burning. But definitely, steam in cold climates, we need to be careful about when we use it and the rate that we use it, and need to consider possibly switching it out with some other media in cold temperatures.
I worked with a plant in Sarnia, and they called me one evening many years ago, and they had basically managed to produce an ice plug that plugged off about 90% of the flow area of the inside of their flare tip, and they actually solved it by pumping methanol into the upper steam ring, and the methanol mixed with the ice plug, and dissolved it over a period of time after pumping it over for a long time. But ice in a center steam can be a big problem if you're in a very cold environment. So.
What are we looking at in the photograph here? Besides lots of ice coming down from the flare tip, I'm assuming that's caused by center and upper steam.
Yeah, that's probably probably the lower tubes, right?
Yeah, this is probably a system with lower steam injection tubes, where you're injecting steam through tubes to mitigate noise and to get higher efficiency. And those tubes are typically cold and have cold gas around them, so they condense that steam very quickly. And to mitigate that, you have to use higher rates, or, as Doug said, you have to switch to an alternative medium, such as nitrogen or something else, to instead of steam during very cold environments, very cold conditions.
Okay. Also, on the subject of cold climates, what are the different types of flame failure detection techniques available, or that you would recommend to ensure 100% availability of flames at all times? Or I assume that means pilots at all times.
Yeah. So we have several different modes of checking or watching our pilots to make sure that they're lit. Thermocouples being the primary one, just because of cost and its robustness, consistency. So thermocouples are a great way to handle that. They're now, retractable systems, so that if they were to burn out, they can be replaced online. So that's a great way to go. We have also flame ionization is an option. Flame ionization is just an electrical circuit that's the path's completed through the flame. So that works well. A little susceptible to some weather occasionally, but otherwise it works well. It's fast. Let's see, optical wise, we have lots of FLIR type cameras on the market that can look at flares and pixelate the individual pilots, but a lot of times those may require multiple cameras to look all the way around a larger flare. And then I think we have some other methods, Clayton. I think the fire eye,
the verify,
yeah.
So we find customers looking for 100% online availability and reliability. Something that can be maintainable or replaceable while the flare is online. And then another aspect that customers are there's momentum behind this request is that it's instantaneous in its identification. And by identification, we need to know the status of the pilot separate from the flare flame. We don't want to have a false positive of, I see a flare flame, I'm good to go, when something could be wrong with the pilot and that needs to be identified. So with a Verify, it's a fiber optic detection device. We've coupled fiber optics, which allow us to speciate between the pilot and the flare flame, but we take it to grade, so you have the instantaneous feedback of an optical system, and it's a non-contact device. The fiber optic's not in contact with the flame, and very, very durable that way. We hope to provide some added robustness or durability, because thermocouples are great and they're still probably the number one method, but thermocouples and flame rods have to be in flame contact. And by being in flame contact, they're just not going to last forever. We make them robust and durable, but not forever.
Hey, gentlemen, I don't hate to interrupt, but we have just about 5 minutes left of discussion here. So why don't we go ahead and do a question from radiation considerations and one from flare maintenance, and then we'll go ahead and close out.
Under radiation considerations, why don't we take the second question, which are what are the major factors to be considered for the location of the flare? Implicitly in that with regard to flame radiation.
So that is one of the biggest factors for selection of flare location and stack height is the radiation that's generated from the flame, from the flare flame. So thermal radiation, some percentage of that heat release is transmitted by thermal radiation to objects at a distance, points of interest at grade. So we have to be conscious of what those levels are so that we don't hurt equipment or personnel. Most flare systems are designed for 1,500 BTUs per hour per square foot radiation level at grade, where personnel could potentially be working. So that is that gives them a few minutes to get away if they're properly dressed in plant working attire. They can quickly move away and not incur any injury from being exposed to that radiation. So maybe a big sterile area around the base of the flare stack's pretty common. Maybe it's just noted that you shouldn't go there, or maybe it's fenced in. It can get very complex. Prevailing wind directions need to be considered because as the flame lays over, that's going to move the radiation points of interest maybe closer to where personnel are, or preferably positioned so that it's away from where personnel will be if possible. So yeah, go ahead.
One major item you need to consider is, as Doug said, the common practice is to size for 1,500 BTUs per hour per square foot at grade on personnel. Keep in mind those personnel at grade can pretty easily move away from, they can move at 90 degrees to the flame direction. They can get away pretty easily, but you've got to also, a big factor is to look at elevated points that are near to the flare itself, like a process tower, the top of a cooling tower, anywhere where the personnel might be restricted in their ability to escape and look at the radiation. Another thing I've seen in a couple of instances is people ignore power lines, elevated power lines that are near the boundary of the plant, and they forget to consider radiation on those types of materials that may or may not be part of their facility.
Right. All right. Well, I'll take one question under the last topic of flare maintenance, and I'll pick on the second question in this category, which is how do you maintain flare tips without a shutdown? And Scott, you want to take this one?
So the video we're showing is a flare system type that we call a demountable system, and it's actually a system that's designed to have a single major support structure with multiple flare stacks all supported off that same structure. And the flare stacks are designed in sections, flanged sections, to facilitate lowering the flare tip in one stack all the way down to the grade, for maintenance access and inspection. Most of these systems are set up with something like a high pressure, a low pressure, an acid gas, and a spare flare. So the spare flare, you can take any of the flares, the normal flares, out of service and divert to the spare flare, and lower that flare tip down to grade for maintenance or inspection, and never shut down your facility. So it's a fantastic advantage for LNG plants or facilities that need to operate for 10 years or 15 years continuously, and depending on the market conditions, and allow your normal flare maintenance to take place. And this is depicting the stack sections being added and then lifted with a local winch system that jacks that flare tip up to the required elevation.
These are also popular for tall elevated flare systems in remote locations, because you can lower one complete flare system or stack down to grade using that winch and tilting and canning system without the use of a tall crane. And so in some places where we have these systems, bringing in a crane sufficient to access the flare tip at 180 or 200 meters means you're importing a crane into the country. Well, this allows you to do maintenance without the use of that expensive crane. And also, you may note in the video, the areas where personnel are working down around the base of that derrick structure are protected from thermal radiation by radiation shielding over the working platforms and working areas. So it's one way, it's a slick way to do maintenance on a flare system without taking the plant out of service.
I guess a second answer to this question would be to potentially hire Red Adair or someone similar to go up while the flare is online in a fire suit, which I've actually seen a couple of times. I'm not sure how the liability insurance would be set up for a plant that would allow that, but regardless, it might be a second answer to the same question.
Well, probably best used in locations without lawyers. And an alternate to that, also, depending on the plant size and capacity, you can also utilize a rental flare to divert the flare header flow to while you're doing maintenance on the flare as well.
Go
ahead.
I was going to say, in the flare replacement business or flare tip replacement business, I wish everybody had the T's and block valves, so that when something came up and the emergency happened, that would allow them to divert to the rental flare, because we've got the equipment that's flexible, various in size and capacity to keep the plant online while these emergencies undergo. The biggest hurdle is not having the ability to divert from the permanent flare to the rental.
And we've supplied rental flares up to 100 meters tall and 54 inch or 60 inch in diameter as temporary flares. Most rental flares are 24 inch and 150 foot height, but definitely there are opportunities for very large ones to be applied if necessary.
Yeah, as you say, the one Scott's referring to, we had in service for 6 months that allowed an ethylene plant to continue operation while their multi-point ground flare was being serviced. Well, I apologize, guys. Clint is giving me the hook here. He's giving me the signal that we need to wrap this up, that we're out of time, and apologize that we didn't have time to address everyone's questions today. And our team will be reaching out and responding to you individually if we didn't get to your question. And we hope that the discussion here today will help you mitigate or eliminate the issues that you may experience with regard to flare systems in the field. And I would encourage everyone, if you have additional questions, comments, or you just have feedback for Zeeco, please fill out the form on this webpage, and we invite you to submit any topics you'd like our experts to discuss in future editions of our Thought Leadership Forum. And want to say thank you again for joining us today for the first episode of our series. We hope you enjoyed the event as much as we did. I didn't know exactly how this would go, but this was actually a lot of fun for me, and I think at our end. And please be sure to follow us on social media to stay up to date on future Thought Leadership Forum events and series, and any other technical topics of interest that we may have available. Those are all out on our social media. And we look forward, as I'm sure everyone does, to the final end of the pandemic and to being able to see all of you and see our friends in person, face to face. And for all of our customers, I just want to say again, thank you for your support during the pandemic, and thank you for your business. And we're going to sign off and appreciate it. I'll say thank you once again.
Okay. Bye-bye.
Appreciate it, everybody.
Thank you, everybody.
Thank you.
Thank you.